Let's warm up by rationalizing the numerator. So that means we want to get the radical out of the numerator. Now we could do this question by multiplying by the cubed root of 18 twice. This will be the long method. So we'll go through it first, but it's probably not the method you want to use. However, if you don't remember the other way, just know that it will work this way. So we're trying to make a perfect cube, so we'll make 18 cubed in the numerator here. And in the denominator, we have the square root of 2, and we have the cubed root of 18 squared, which is 324. And in the numerator, we have rationalized it, it's 18, and in the denominator, we've got root 2. Now, this might have a perfect cube in it, so we need to break 324 down into 2 and 162, 2 and 81, 9 and 9, and 3 and 3 and 3 and 3. 2 2s, and there is a perfect cube right there. So let's get that out. We're going to get the cube root of 27, which is 3, and then everything else in here, 2 times 2 times 3 is 12. And now we can simplify the 18 divided by 3 and get 6 over square root of 2 cubed root of 12. So that worked. Let's try a different method where we won't create something that we have to simplify. So I'll put over here. Cubed root of 18 over root 2. Now if I wanted to make a perfect cube in here, then I can actually just analyze what the factors of 18 are. And they are 2 times 3 times 3. So to make a perfect cube, I need one more 3 and 2 2s. So if I just multiply by that instead, which is 3 times 2 times 2 is 12. So I can multiply by the cube root of 12. And then in the numerator, we get the cubed root of 18 times 12, 216, or 6 cubed. And in the denominator, we just have a root 2 in the cubed root of 12. Simplify the top, and we're done. So in this step, if we can figure out what we need to make a perfect cube, we won't need to simplify at the end. 5.3 radical equations. We're going to solve radical equations and just those that have square roots. Remember, when we're solving radical equations, identify any restrictions on the variable and identify whether any of the roots you find algebraically are extraneous. Let's look at how we will find restrictions. First, we look at the index of the radical. If the index is even, we set the radicand greater than or equal to 0 if we want real numbered results. So 7x minus 21 is greater than or equal to 0. Add 21 on both sides. 7x is greater than or equal to 21. Divide by 7 on both sides. X is greater than or equal to 3. If we had an odd index, then it doesn't matter what's in the radicand, positive or negative, so our variable can be any real number. Now if we have something like this, we've got to look at the two radicals independently and then compare the restrictions to find an overall one that works for both. So for our first example, we've got a square root, so x minus 5 needs to be greater than or equal to 0. Add 5 on both sides, we get x is greater than or equal to 5. For the denominator, normally we would have x plus 5 is greater than or equal to, but it can't be equal to 0 because it's in the denominator. So subtract 5 on both sides, we get x is greater than negative 5. Then we will put this on a number line so we can visually see what we're going to end up with. X is greater than or equal to 5, and x is greater than negative 5. We see that they're both satisfied in this interval here, so this is our overall restriction for our variable. We can't have this interval, we can't have one radical working and one radical not working. This one, we've got x minus 2 needs to be greater than or equal to 0. Add 2 on both sides, so x is greater than or equal to 2. In the denominator, we've got 5 minus x is just greater than 0, not equal to, because again it's in the denominator. Solve this one, let's add x on both sides, so x is less than 5. Put this on a number line so we can visually see what's happening. Greater than or equal to 2, and less than 5. We see that the interval that where both radicals will work are in between here. So we get 2 is greater than or equal to x is less than but not equal to 5. And that would be our overall restriction for this. Example 1 is solving this radical equation right here. We're going to start off with restrictions because we want real number answers. So x plus 3 needs to be greater than or equal to 0. Subtract 3 on both sides. That means x needs to be greater than or equal to negative 3. Now let's actually solve the radical equation now. First step, isolate the radical. Second step, get rid of the square root by squaring both sides of the equation. Next step, solve for the variable. And last step, we want to verify and check that our solutions work. So isolating the variable, we should probably subtract 4 both sides. X plus 3 is equal to 3. It's isolated. Next step, get rid of the square root by squaring both sides. Squared, squared. On this side we get x plus 3 and it equals 9. Subtract 3 on both sides, and we get x equals 6. Looks good. Let's verify it by putting the value into our equation. 6 plus 3 plus 4 equals 7. This would be the square root of 9 plus 4 equals 7. And that's 3 plus 4 equals 7. And 7 equals 7. This looks like a great, legitimate answer. Example 2. I'm going to state the restrictions so that this will give us real numbers only. So x squared minus 4 needs to be greater than or equal to 0. Let's add 4 on both sides here. Get rid of that. X squared is greater than or equal to 4. We could square root this. And remember, if we square root a variable squared, we're going to get plus or minus. Square root this side, we get 2. Now we have two cases. We've got a positive case and a negative case. So two cases. Positive case is x is greater than or equal to 2. That's fine. Negative case is negative x is greater than or equal to 2. Divide both sides by negative 1 or multiply both sides by negative 1 to move the negative over. When we do that, we will flip the inequality. So here we go. It will work when x is greater than or equal to 2, and it will work when x is less than or equal to negative 2, but it won't work in between those two values. So those are our restrictions. Now let's get on to solving the actual equation. Remember, that was just for the restrictions. x squared minus 4 is equal to 6. Looks like we've already isolated the radical, so we can square both sides. This side we get x squared minus 4, this side we get 36. Add 4 on both sides, we get x squared equals 40. Take the square root of both sides. This time we got a variable squared, so we get plus or minus x equals the square root of 40. Now we can simplify this somewhat. X equals plus or minus 4 is in here, so the square root of 4 is 2. And if we divided out 4, we'd be left with 10. So we could write it like that as a mixed radical. And there's our solutions. But let's give those a try back in the original equation to see if they are good solutions or not. So we've got the square root of x squared. I'm going to verify both at once because really I'm going to square the x, and so it doesn't matter if it's plus and minus, it'll work. And I'm going to use root 40 because that's easier to square. So I've plugged both of my solutions in. The square root of 40 squared plus or minus is positive 40. And 40 minus 4 is 36. And the square root of 36 is 6. And both of those solutions work. Example 3, let's start off by finding the restrictions on x. Now we only care about what's under the radical here. 2x plus 3 needs to be greater than or equal to 0. Subtract 3 on both sides. And divide by 2 on both sides leaves us with x is greater than or equal to negative 3 over 2. Let's actually solve the equation now. We got x minus root 2x plus 3 is equal to 6. We need to isolate this radical. You can move this radical over here, move the 6 over here. You could just move the x over there. Either way, we'll get it by itself. Let's say the most common would be maybe subtracting x on both sides. Negative 2x plus 3 is equal to 6 minus x. Now we've isolated the radical. It does have this negative sign in front, but I really don't care about that, because when I square it, it will disappear. So I'll square both sides. On this side, again, the negative will cancel, the square root will cancel, and I'll just be left with 2x plus 3. On this side, remember I have to square the binomial, not the individual terms. So 6 times 6 is 36. 6 times negative x is negative 6x, and negative x times 6 is negative 6x again, so negative 12x. And then negative x times negative x plus x squared. If you can't do that in your head, make sure you write out both binomials and show each step. Now let's collect up like terms onto one side. This side has a positive leading coefficient, so I'll put everything on this side. So we've got an x squared. We've got a minus 12x minus 2 more x's. So that's minus 14x. And we've got plus 36 minus 3, and that is plus 33. Now, there's various ways to solve this. The quadratic formula, factoring. Looks like we could probably factor it because 3 and 11 multiply to 33, and the negative add up to that. And so we can see that x needs to be equal to 3 to make it 0, or 11. So there's my two solutions. Now we need to verify. Make sure those are good solutions. So everywhere where we see an x, let's first try 3. X equals 3. So we got 3 minus 2. 3 plus 3 equals 6. And this is 6 plus 3 is 9. equals 6, and the square root of 9 is 3. So we actually get 3 minus 3 equals 6, and no, it doesn't. So that doesn't work. So 3 is extraneous. Extraneous. And that means that it's an algebraic solution that we found, but that doesn't actually work. And it doesn't work in this case because we only take the principal square root. So we'll cross this one out and we'll write extraneous. Whenever you're solving algebraically, you must show this solution and then show that it will not work. Let's check the other one, 11, make sure it works. We've got x equals 11 now. 11 minus 2 times 11 plus 3 equals 6. 11 minus, that's 22, 22 to 25. And 11 minus 5 does equal 6. And so 11 is a good answer, a good solution, and our only solution to this equation in this case. Example 4, we actually have the same radical as last time, and so our restriction will be the same. X needs to be greater than or equal to negative 3 over 2. Let's get on to solving this. X minus this radical, and on this side I'm going to distribute in the 3 over 2. So it equals 3x over 2 plus 3 over 2. Next we need to isolate the radical, so we'll subtract x on both sides. On this side we've got x over 2 plus 3 over 2. Ready to square both sides. On this side the negative and the radical will cancel, and we'll just be left with 2x plus 3. On this side, maybe it would be helpful if we rewrote it like two binomials instead. Then we could see how we're going to use the distributive property here. So x squared over 4 plus 3x over 4 plus another 3x over 4, so 3x over 2, and plus 9 over 4. Now, I don't like working with fractions, so I'm going to multiply both sides by 4 to get rid of those fractions. So distribute in the 4, we get 8x plus 12 is equal x squared 6x plus 9. Now we want to collect up all the terms on the same side. So subtract 8x on both sides, subtract 12 on both sides. We get 0 is equal to x squared minus 2x minus 3. Now we need to solve this quadratic. We could do that by factoring with a quadratic formula. This one looks easy enough to factor, so we'll solve it that way. X minus 3 and x plus 1. Which means that our two solutions are 3 and negative 1. Next step, we need to verify. So let's go back up about here and verify, starting with the x equals 3. We put x equals 3 into the original equation, so 3 minus the square root of 2 times 3 plus 3 equals, this was 3 over 2 x plus 1. Okay, so keep everything on one side that was on that side. Don't cross over, right? When you're verifying, evaluate this side independently and evaluate this side independently and see if they're equal. So 3 minus, this is 6 plus 3 is the square root of 9. And on this side, this would be 4. 4 times 3, no, I'll do that in 2 steps. And this is 3, so 3 minus 3 is 0. And this is 12 over 2, which is 6. Well, that didn't work. So that one is not a good solution. Let's try the other solution, negative 1. we have negative 1 minus 2 times negative 1 plus 3 is equal to 3 over 2 negative 1 plus 1. On this side we got negative 1 minus, this is negative 2 plus 3 is 1. And on this side I've got negative 1 plus 1 is 0. So this whole side would just be equal to 0. And this one would be negative 1 minus 1 not equal to 0. It's negative 2. So this solution is not good either. That means that both of our solutions are extraneous. Example 5, we now have two radicals. So when we do our restrictions, we're going to have to look at them both. First we'll do this one. 4x plus 5 needs to be greater than or equal to 0. So 4x needs to be greater than or equal to negative 5. Divide both sides by 4. X needs to be greater than or equal to negative 5 over 4. Now we need to look at this one. So 2x minus 1 is greater than or equal to 0 as well. Add 1 on both sides. And divide by 2 on both sides. X is greater than or equal to 1/2. Let's put it on a number line so we can visually see what's happening here. We've got negative 5 over 4, and we've got 1/2. One of the restrictions is like this, and the other is like this. So where are they both satisfied? In this interval. So we use x is greater than or equal to 1/2. Now let's solve the equation. But you notice our first step was isolate the radical, but now we have two radicals, and so we can't isolate them both. So I'm going to square both sides. And you can move this one over and square both sides and get rid of this radical and then isolate this radical. Either way, we're going to have to square this equation 2 times to get rid of two different radicals here. I'll leave it like this and just square both sides. I'll rewrite this because there's a lot of confusion. A lot of students think you can just square the individual terms, which you cannot. We have to use the distributive property when we're squaring binomials. So it's like this. So the whole binomial times the whole binomial equals 4. Okay, so we've got root 4x plus 5 times root 4x plus 5. That would just be 4x plus 5. Then we got this root times this root, and once again here and here. So this would be minus 2 times the square root of 4x plus 5 and 2x minus 1. And last is this term times this term, so positive, and the 2x minus 1 is freed up. Now you notice we still have a square root here. So we didn't get rid of it the first time. Let's collect up like terms and isolate the last remaining radical here. So let's subtract 6x on this side. So minus 6x minus 6x. And on this side we got minus 5. Well, actually we got plus 5. Minus 1 is 4, so minus 4. We'll get rid of it and move it on to this side. Now that's nice because now we have 4 minus 4. Well, a lot going on there, but what we have left on this side is the radical. It does have a coefficient, but that's okay. I'm going to distribute this in. Okay, so we get 8x squared minus 4x plus 10x minus 5 and on this side I get negative 6x. And we can now divide both sides by negative 2 to further simplify it. So we got 8x squared plus 6x minus 5 is equal to 3x. Now I can square both sides. Make sure to put brackets around that, or you're only squaring the x. That wouldn't be right. On this side, the square root and the square cancel, so we're left with 8x squared plus 6x minus 5 and this would be 9x squared. I'm going to throw everything on this side, so minus 8x squared minus 8x squared. That way I'm going to have a positive leading coefficient. Minus 6x minus 6x plus 5 plus 5. Nothing's left on the left side, so 0 equals x squared minus 6x plus 5. And now we just have a quadratic to solve. You can use any method you want. Looks like we can factor this one. X minus 5 and x minus 1. So x would be 1 and 5. Now let's verify. X equals 1. Our equation would look like 4 times 1 plus 5 minus 2 times 1 minus 1 should equal 2. 4 plus 5 is 9, so root 9 minus, this is just 1, and this is 3 minus 1 is 2, and it sure is, so this is a good solution. Let's verify our other solution that we found, x equals 5. We got 4 times 5 plus 5 minus 2 times 5 minus 1 should equal 2. This is 25 altogether, minus 9, the square root of 9, and this would be 5 minus 3 equals 2, and it does equal 2. That means that both of our solutions are good solutions. Example 6, we want to write and solve a radical equation to find a positive real number that exceeds its square root by 6. So we need a variable. How about x? And it's a positive real number, or in other notation, it's greater than 0, and it's real. So we have a number here that is equal to 6 more than its square root. So let's isolate the radical. How about minus 6 on both sides? X minus 6 equals the square root of x. Square both sides. Remember, square the whole binomial. So x squared minus 6x minus another 6x minus 12x plus 36. Do not just square the individual terms. You have to square it like this. And x, the square root of x squared is just x. Collect up like terms, so I guess I'll move it to this side. Minus x minus x. We got x squared minus 13x plus 36. Again, we're solving a quadratic. This one looks easy enough to factor as well. We can factor x minus 9 and x minus 4. That means that our solutions are x equals 4 and 9. Now, so this is saying that two numbers might do this. Let's verify to make sure. X equals 4 first. Let's put 4 in our equation, so 4 equals the square root of 4 plus 6. 4 equals, square root of 4 is 2 plus 6, that's 8. So that does not work. So 4 is extraneous. Now let's check if 9 works. Got 9 is equal to the square root of 9 plus 6. And that does work. Square root of 9 is 3, 3 plus 6 is 9, and this is just fine. This was part of Algebra and Number 3, solve problems that involve radical equations, limited to square roots. There's some questions from the textbook. Try them out, see if you know what you're doing.